Hello mathematicians, thank you for joining me today. What we're going to work on today is we're going to look at the set of all mappings from the real numbers to the real numbers. And what we want to show is that if we combine this with the operations of mapping, addition, and multiplication, that we end up with a ring. So we're going to show that under addition we have an abelian or a commutative group, and under multiplication we're going to have a semigroup. Alright, so to begin with, what we want to look at is the set of mappings from the real numbers to the real numbers under addition, so we should give a formal definition of what addition is. In particular, what we have is, if we have two mappings from the real numbers to the real numbers, say f and g, then we're going to define f plus g as the mapping which sends x to f of x plus g of x. And so it would be the normal addition for mappings on the set of real numbers. Now with this, we're going to have to show that this is closed, or that is that when I take f plus g, I again get a mapping on the real numbers. I'm also going to have to show it's associative. I'm going to have to show it's commutative. I'm going to have to show there's an identity, and I'm going to have to find inverses for every function. Alright, so now what we're going to do is we're going to show that my set of mappings on R is indeed closed under this defined addition. And so what that means is if I take two mappings, f and g, and add them together, I get another mapping. Now, I've outlined the proof for here already, so I'm just going to walk through. The idea is that if we want to show that the addition of two mappings, or the sum of two mappings is again a mapping, what we have to show is that for every x that's a real number, then f plus g of x is again going to be a real number. That is, it's going to send everything in the domain, which is the real numbers, to something, a well-defined something in the codomain, which is also the real numbers. Now, if we just use the definition that we gave for f plus g, well, f plus g of x is f of x plus g of x. So what we have is, I know that f of x is well-defined because it is a mapping on R. I know that g of x is well-defined because it's a mapping on R. So f of x is a real number and g of x is a real number. But we also know that the real numbers are closed under addition. Therefore, if I take a real plus a real, it's going to end up being a real number. So really, this is just the outline showing that, well, f plus g takes x and sends it to a real number. Therefore, f plus g will indeed be a well-defined mapping on the set of real numbers. Now we need to show associativity. And so what I want is I want to take f plus g plus h and show that that's the same thing as f plus g plus h. Now I have the proof outlined here so that we can run through it, but the idea is that I would just start off with f plus g plus h and an element of the real numbers. And I would see, what does this mapping do to x? Well, what it does by definition is I'm taking f plus g plus h, so that should be f plus g of x plus h of x. But now if I continue my definition, this is just f of x plus g of x plus h of x. And so what I get is that f plus g plus h of x is just f of x plus g of x with the parentheses here plus h of x. Now, however, I want to point out each of these is a real number where I'm adding up real numbers. So for the real numbers, they satisfy associativity. So what I get is that, well, f plus g plus h is the same as f plus g plus h in parentheses. So again, using the associativity of real numbers, I get that. But what I get here is then, well, this is just g plus h of x, and this is f of x. So I get f of x plus g plus h of x, which is just f plus g plus h in parentheses of x. And so what I've done is that shown that f plus g plus h is the same as f plus g plus h for all x in the real numbers. Therefore, those two functions are equivalent. So we do have associativity for the addition of mappings on R. Now, if we work with commutativity, we're going to have a very similar proof, except for we'll only have f and g are mappings on R. And so we're going to show that f plus g is the same as g plus f. So we take any real number and we show that the image of that real number is going to be the same in either direction. So now if I start off with f plus g of x, by definition that is just f of x plus g of x. So now last time we used associativity of real numbers, but now we're going to use commutativity of real numbers and show that, well, this is a real plus a real. the order doesn't matter for addition for real numbers, so f plus g is the same as g plus f. So then by definition, this is just g plus f of x. So I indeed do get f plus g is g plus f. So I have that the addition of mappings is a commutative operation. Now we're ready to find an identity mapping. And so because it's addition, what we want to think is what would an identity look like? And so the identity for real numbers addition is 0. So what I want to think about is, can I find a function that behaves like a 0? And so I'm actually going to define my 0 function, and I'm just going to define it as 0 of x is 0. So that is, this mapping will take any real number and map it to 0. And so if I take that, and I take any other mapping and add the 0 mapping, then f of 0 plus 0 of x is just going to be f of x plus 0 of x, which is f of x plus 0. Now, since we know that any real number plus 0 is just the same real number, we get out f of x. And so what you notice is that for my definition of 0 of x, any mapping plus that mapping is just going to be the original mapping. So f plus 0 is indeed just f. Now, we've already shown commutativity, so that would mean that also f plus 0 is 0 plus f is f. So therefore, we do have an identity for the addition on this set. Now that we found our additive identity, we're ready to find our additive inverses. Now, when we looked at our identity, we noticed that the additive identity for real numbers was 0, so we tried to find a 0 function. In the same way, if we think about additive inverses for real numbers, well, the inverse of a would be negative a, because a plus negative a is 0. So what we want to do is, for any function f, we want to say, okay, well, let's let g be negative f of x, so that hopefully when we add those together, we get out the 0 function. So if I define g to be negative f of x, then what we notice is that f plus g of x is, by definition, f of x plus g of x. But g of x is just negative f of x. So what we have is a real number plus negative that same real number. So in the real numbers, that just gives me 0. So what that means is that f plus g of x is 0 for all x. So that is just the 0 function that we defined as the identity. Now, because f plus g is the identity mapping, we get that these will indeed be inverses as long as we can show the other direction. But now, because we have f plus g is 0, notice we've already shown commutativity. So g plus f is equal to f plus g, which is the additive identity on the set of mappings of real numbers. Therefore, we do indeed get that the negative f of x is the additive identity of f of x. All right, we've now shown that the set of mappings of real numbers under addition is closed. So that is, the addition is indeed an operation. It's an associative operation. It's a commutative operation. Furthermore, there exists an identity, the 0 mapping, and every mapping has an inverse, namely the negative of that mapping. So we have that this set under addition does indeed form a commutative or abelian group. Now, to finish our proof, what we end up wanting to show is that the set of mappings under real numbers in addition and multiplication is going to form a commutative ring with identity. That means that, well, we already have that it is an abelian group under the addition, so we have to show that this set under the defined multiplication, that is f times g of x, is f of x times g of x. Then what we want to show is that this is, well, we have to show that this is an operation. So that is that this set is closed under this product as we defined it. Because we want it to be a ring, we need it to be a semigroup, so that is, this should be an associative operation. Because we want to have an identity, this will end up being a monoid, so we should have an identity as well. And because we want it to be a commutative ring with identity, we're also going to have to show that this product is commutative. Now what we want to show is that we do indeed have an operation for this product. So I'm going to let f and g be mappings on R, and I'm going to say let x be an arbitrary real number. And what's going to happen is if we take f times g of x, by definition, that is just f of x times g of x. And so now the goal is to show that we end up back in the set of real numbers if we start in the set of real numbers. Therefore, what we notice is that f times g of x is just f of x times g of x. But because f is a mapping on the real numbers, f of x is real. g of x is a mapping on real numbers, so g of x is real. So what we have is the product of two real numbers, and because the real numbers are closed for multiplication, we do get that f times g is again a real number. So what we have is that f times g of x is again a real number, so f times g is going to be a mapping on the set of real numbers. Alright, so now we're ready to show associativity. So what we have is we'll let f, g, and h be mappings on the set of real numbers, and we'll let x be a real number. Then we have to show that f times g inside parentheses times h is the same as f times g times h, where the g times h is inside parentheses. And that means that f times g times h of x is equal to f times g times h of x for all x in the set of real numbers. So now in order to show that, we're just going to start with one side. We're going to try to simplify and get out the other. So notice that f times g times h by definition is f times g of x times h of x, because we're taking the product of this function and this function. Now because I have f times g, that is just f of x times g of x, so what we end up with is f of x times g of x times h of x. But now notice that these are all real numbers, so what we can do is we can use the associativity of real numbers multiplication, and we get that this is just going to be f times g times h. So now, again, if we continue with this, that is just f times g times h of x. So we do get that f times g times h is the same as f times g times h. So we do have associativity for the product of mappings on the set of real numbers. In order to show commutativity, we now have to say, well, let's let f and g be mappings on R, then f times g should be g times f. Well, if we just want to show that, we have to show that f times g of x is equal to g times f of x for all x in the set of real numbers, so we let x be real. Notice that f times g by definition is just f of x times g of x, but now these are real numbers being multiplied together, and we know that real number multiplication is commutative, so this is just g of x times f of x. But by definition, that's g times f of x, so indeed we have already shown that f times g is just g times f, so we do have a commutative operation. Now the last thing we need to show is that we do have an identity for the multiplication. So the way we did this when we had the additive identity was we said, well, the additive identity for real numbers was 0, while the multiplicative identity for real numbers is 1. So what we're going to do is define a function 1 of x, where 1 of x is equal to 1 for all x in R. And what we want to do is show that that acts like an identity for the product of mappings. So if I take any arbitrary f in the set of mappings on real numbers, and I take f times 1 of x, I want to show that that's equal to f of x. But f times 1 of x is just f of x times 1 of x, but 1 of x is just 1, so we get f times 1 of x is f of x times 1. But now f of x is a real number, so a real number multiplied by 1 is just the original real number, so we just get out f of x. So indeed what we get is that f times 1 of x is f of x. Now we should show the other direction as well, but we just showed commutativity. So 1 times f is the same as f times 1 is f of x. So we do indeed get that the mapping we define, 1 of x is equal to 1 for all x, is the identity for products on the set of all mappings in real numbers. So now just to recap everything we've done, we showed that the set of mappings on real numbers under addition was, well, the addition was an operation, it was associative, it was commutative, there were identities, and there were inverses. So we get that the set of mappings of real numbers under addition is indeed an abelian group. Now, if we looked at the set of mappings on real numbers under the product, what we noticed was that, again, this was an operation, it was an associative operation, it was a commutative operation, and identities did exist. So this would be a commutative monoid. So if we use both of these operations together with the set of mappings on real numbers, what we get is that that is indeed a commutative ring with identity. Thank you for joining me today. I hope you found this video helpful. If you did, make sure to like the video and subscribe to the channel.